Welcome. In this video, we're going to demonstrate some applications into problem solving, in particular with relation to transformers. So here I've extracted problem 44 from our OpenStax college physics book, and as an example, so we're going to take a look at how to approach problems. Problem 44 says a plug-in transformer like one in a particular figure in the book. You're welcome to view that. This transformer supplies 9 volts to a video game system. Now, how many turns are in its second coil if its input voltage is 120 volts and the primary coil is 400 turns? That's the first part of the problem. And the second part is, what is its input current when its output is 1.3 amperes? Okay, so first things first, the transformer attaches to a wall, to a source, and that source supplies the transformer with a voltage of 120 volts. So be careful, this 120 volts is one that goes into the transformer, and then this 9 volts is what the transformer supplies to a device connected to it, which here is a video game system. It could be an Xbox, it could be a PS5 or whatever it is. The point is, the wall plug onto which the transformer is connected to pushes out 120, but then the transformer transforms that voltage to a new value or to a new amplitude of 9 volts. This 9 volts is then passed on to our component. This is quite common, especially with your laptops. If you go from one airport to another airport, one country to another country, the brick in your laptop charger is responsible for doing this, the job that's being done by this plug-in transformer. Okay, now enough theory, let's see how that looks. Remember, here, part A is concerned with we can determine the turns on the secondary coil by using the voltages. So let's first note that on the secondary side, the voltage is 9 volts. This then means the primary side, the side that's connected to the source, is 120 volts. Then we are interested in determining the number of turns on the secondary side, and we're informed about the number of turns on the primary side, and that is, we were told, is 400 turns. Then from the law of transformers, we know that this ratio is a constant across the transformer. In other words, the ratio of the voltage to the number of turns is going to be equal, on the primary side, is going to be equal to the volt over the number of turns on the secondary side. What we're interested in is this N sub S, so we shuffle our equation around and we determine that that the number of turns on the secondary side is related to the number of turns on the primary via this ratio, which ratio is going to be 12 divided by 400, multiply this by, I'm sorry, not 400, I'm mixing up my values here. That should be, the secondary side is 9 volts, and then the primary side is 120 volts. I'm sorry about that. And then the number of turns is, on the primary side, is 400. Then we're going to get some value here, which I will not compute numerically. You're welcome to punch in the numbers and post them in a comment section, just to check if we're getting the same answers. Now, conceptually, this is sufficient. We have, in principle, the number of turns. You might find, for instance, a number that has decimals. Um, this means typically you might have to round it to the nearest integer. Because remember, the number of turns is actually, at least a physical number of turns must be an integer number. It is impossible to do a number of turns that's 1.0012. That doesn't make sense, at least physically. So yeah, so the point is, if you find numbers that have decimals, it is wise to round them off to the nearest integer so that the number of turns is something that is physically achievable. Okay, that's sufficient for that part. Now let's move on to part B. Part B, we're asked to determine what is the input current, given that the output is 1.3. So we are clueless about the primary side, about the current on the primary side, but we are informed about the current in the secondary side. This is 1.3 amperes. Okay, now we can determine the primary side given that we know the turns ratio. Here we have a few luxuries, but they all will amount to the same thing. I will simply use this. That is this is the law of transformers for current. This is the law of a transformer for currents. Then this will mean IP. This is the primary current on the primary side is going to be NS divided by NP times IS. NS over NP is equals to VS over VP. Remember, from this, we can make NS over NP the subject of the formula. What we will obtain is that NS over NP is just VS over VP. So we can substitute that in there and find that this is going to be VS over VP times IS. Now we have already computed this, right? We do know these values. So we could just punch them in, and we know the current here, and we could determine what the current on the primary side is going to be. And that looks like this. The voltage on the secondary side is 9 volts. The voltage on the primary side is 120. And the current on the secondary side, we were informed that this is 1.3 amperes. So it would appear that this is our finding. Of course, over here, you can still punch in the numbers. I will not do it numerically. But what do we learn about this transformer? Notice this transformer took 9 volts and, I'm sorry, it took 120 volts. It took 120 volts and converted it to 9 volts. It took 120 volts and it converted it to 9 volts. You remember what kind of transformer does this? It's called a step-down transformer. Step-down transformer. And what we know about step-down transformers is that while they step down the voltage, they actually amplify the current. In other words, the current on the primary side is going to be less than the current in the secondary side. And as you can see here, we have 1.3, which is the current on the secondary side, but this secondary side is being multiplied by a number that's less than 1. So we know that IP is going to be less than IS. So this essentially is a step-down transformer, and this is exactly how you would approach this problem. Okay, I'll stop here for now. I'll see you in the next one.